Naming binary ionic compounds or type 1 compounds. There is a lot of power in naming things. IUPAC stands for the International Union of Pure and Applied Chemistry. That gives us rules for naming things, and those names are descriptors that let us know what a molecular structure is. So naming tells you what that formula is and how those molecules are put together. So when we get with a binary compound, those are pretty easy. We're going to call these type 1 compounds. Rules for naming type 1 binary compounds are very straightforward. You're going to take the cation first, which is usually that metal. Right? It's a monatomic cation. It's going to take its name from the name of the element. And then you're going to take the name of the anion and stick an IDE on it. All right, so sodium chloride, right? For example, that's your go-to. Right, so hydrogen or lithium or sodium or potassium, you're going to name the metal first, and then your anion, you're going to stick this "ide" ending on it. Hydride, fluoride, chloride, bromide, iodide, oxide, sulfide. So potassium sulfide would be a binary ionic compound. When we build these binary ionic compounds, we know that they're not necessarily going to combine in a 1-to-1 ratio. So if I've got like magnesium fluoride, it's going to be, to balance out the charge, magnesium's a +2 charge, fluoride is going to be a -1 charge. My formula will be magnesium fluoride, but because these guys are nice and regular, we do not need language to indicate the number of fluorine molecules, right? You will know that, okay, this guy's a +2, this guy's a -2. There's only one way I can make magnesium oxide, right, with 1 magnesium and 1 oxygen. There's only one way I can make lithium oxide with 2 lithiums and 1 oxygen. There's only one way I can make sodium chloride with 1 sodium and 1 chlorine. All right, so all of our +1 guys in column 1, all of our +2 guys in column 2. Over here we got -1s for our halogens, -2s for our chalcogens, and -3s for our pnictogens. Down here in the +3, that's aluminum, gallium, indium. Right, you do see some variations down here at the when you start to get down further into that periodic table, but gallium, indium, and aluminum and boron would be nice and well behaved, right? So metals can form cations. Some are going to have multiple charges, like these guys in the middle are transitions. They're going to be weird. A lot of those are going to form more than 1 metal cation. Right? If we do that, we're going to have rules about, well, how do I know if I've got iron with this 2+ charge forming a product with chlorine, and iron with a 3+ charge forming a chlorine product, or copper with multiple charges? We'll talk about that in just a second. Right? So our binary ionic compounds are going to be neutral, with the total number of positive charges equal to the total number of negative charges. So Na+ and Cl- are going to combine to form NaCl. Mg2+ and O2- are going to form MgO, magnesium oxide. Aluminum sulfide is going to be Al3+ and sulfur 2-, and you're going to form Al2S3 to balance those charges out. Pro tip, the drop and swap method works most of the time. So you're going to take whatever this is up at the top, and you're going to drop it. So this was a 3+ on here. You're going to move that 3 over down and by the sulfur. And then you're going to do the same thing with that 2, and you're going to move it down next to the aluminum. So you get Al2S3, right? It's just called the drop and swap method. I mean, it works with these guys too, right? 1, drop it over to the chlorine. 1, you drop it over there to the sodium. Same thing here. You could do it as 2 and 2, but you simplify that to MgO. All right. So let's look at some of these binary compounds. CSF is going to be cesium fluoride, and AlCl3 is aluminum chloride, and lithium with an H is going to be lithium hydride. So in naming our chemical compounds, the chemical formula is considered. And the reverse process is also true. So the formula for calcium chloride is going to be written as CaCl2. Calcium is going to form +2 cations. Chlorine is going to form a -1 anion. So in order to maintain charge balance, when we call it calcium chloride, we know that its formula has to incorporate that charge balance. It's going to be calcium with 2 chlorines next to it. Right? So given the following systematic names, can we go the other way? So potassium iodide, calcium oxide, and gallium bromide. Right? Yeah, of course we can. So potassium iodide is going to be K and an I. Potassium is going to be +1, iodine is -1, it'll be Ki. It's got K plus and I minus. Calcium oxide is going to be CaO, because you've got calcium 2 plus and oxygen 2 minus. Gallium bromide, gallium is going to have a +3 and bromine is a -1, so we're going to need thrice the number of bromines to equal the 3 plus charge on the gallium. So this is our drop and swap, but going backwards. Right? So these are our type 1s, right? These are the super duper easy ones. You think about sodium chloride, you got just our +1s or our +2s as our metals, and then it doesn't have multiple charge states to it. And then you've got something over on the right-hand side that's going to be your anion. It doesn't have multiple charge states to it. Very straightforward. Right? What do you do if you do have multiple charge states? These are binary ionic compounds of the second type. So binary ionic compounds type 2, revenge of ionic compounds. Some metals are going to have more than one positive ion. This results in the formation of more than one type of ionic compound with a given atom. And they have very different physical properties. So the charge on the metal ion is going to be specified using Roman numerals. Right, so it's going to be the name of the metal, and then in parentheses what the charge is, and then whatever the name of the anion is, and they're going to stick IDE on it. Right? There is an older convention that would say the metal with the higher charge is going to be ic, and the metal with the lower charge is going to be us. So the way I remembered this was if you ate too much, you would get ic, right? So it's got the bigger charge is going to be the ic, and then the lower one would be the us. So ferric chloride and ferrous chloride, or cupric nitrate and cuprous nitrate, those would be indicating the charge state. But that's really ambiguous, right? Because I've got ferric, which is +3. It's the high state for iron. And then I got cupric, but that's only a +2. So there's no differentiation to tell you without memorizing what the charges are, whether your ic is going to be a 3 or a 2, or your us is going to be a 1 or a 2 or a 3, or what have you. So putting it in parentheses makes that way easier, right? So this new way of doing it, that's pretty much what everybody does now. You will still see sometimes, particularly in non-chemistry applications, like I could go buy a container of ferric chloride as an etchant for home brewing my own circuit boards, right? If I want to do some circuit board etching. And let's look at some examples. Okay? Binary ionic compounds where we got more than one charge state. So we're going to use this parentheses to indicate that this is iron 3 plus. And so iron 3 plus, this 3 plus becomes an III in here, capital letter I's, Roman numerals. Iron III oxide is going to be iron 3 plus, and then the oxygen is going to be 2 minus, and so our formula will be iron 2, right? We'll do our drop and swap. 2 goes down next to here, 3 goes over there, Fe2O3. Tin 2 chloride, which I think would be stannous chloride. Tin 2 chloride, right, is going to have a +2 charge. Chlorine's going to have a -1 charge. We'll do our drop and swap. 2 goes down there, 1 goes over there. We don't need to write it in there. We end up with SnCl2. Lead 2 fluoride, plumbus. Everybody has a plumbus. A plumbus 2 chloride is going to be 2 plus and an F1 minus. Drop and swap. We end up with 2 fluorines to counteract the charge on the +2 for the lead. Right? We're going to put these in Roman numerals in between. So don't use a Arabic numeral 2, right? Don't do a lowercase I, uppercase I, Roman numerals. Right? If we look at some of these guys that are going to form cations with different charges, chromium, iron, cobalt, copper, tin, mercury, lead, right? It gives the different charge states. You can usually, on a good periodic table, get one that will tell you what these charge states are. Whether it's 2 or 4, sometimes there's even more than that. This one's pretty simplified. And this gives us the older name too, right? So chromus and chromic, and ferrous and ferric, and cobaltus and cobaltic, and cuprous and cupric, and stanic, and mercurius and mercuric, and plumbus and plumbic. Right? So writing out the systematic names for each of these and writing out the formula. If I got manganese 4 oxide and lead 2 chloride, what would those look like? Well, our manganese 4 oxide, we've got 2 oxygen ions, -2 charge. The to balance out the +4 charge on the manganese, so it's going to be MnO2. Our lead 2 chloride, it's going to be a +2 charge on the lead. Chloride's always going to be -1, so it'll be PbCl2 to balance that charge. So our Roman numerals are only used in cases where more than one ionic compound exists, right? So we don't need to do it with our group 1s or our group 2s, right? Don't need to do it for our alkali and alkali earths. Elements that form one cation, we don't need to worry about that. So group 1A, group 2A, aluminum, silver, we don't need to specify and use Roman numerals. Okay? So here's a little flow chart. Does it contain type 1 or type 2 cations? If it's type 1, you name the cation using the element name. If it's a type 2, you use the principal charge balance to determine the cation charge, and you include the cation name, a Roman numeral indicating the charge. So let's look at some compounds and name them. So cobalt bromide, and I got cobalt and bromide. Cobalt's got more than one oxidation state. What are we going to call this? Calcium chloride and aluminum oxide. All right, we've got different names for these, but our systematic name, because cobalt's got more than one charge state, we know that it's going to be +2 to maintain charge balance with our 2 bromides. So we're going to do cobalt in parentheses 2 bromide. Calcium only exists as +2, so we don't need to specify with our Roman numerals. We'll just call it calcium and then chloride. Our aluminum oxide, aluminum only forms +3, so even though our formula is Al2O3, we just need to call it aluminum oxide. So our table of common cations and anions, here's another version of that. Notice that these guys are the type 1s. Our common monatomic anions are over here on the right. And then we've got some nice variability going on with all of our Ds and some of these guys in here. And more than one atom going around as a group and behaving as what we call a polyatomic ion. So polyatomic ions just mean it's got more than one atom acting like an ion. And there's a couple of them. One of the most common groups of these are called oxyanions, and they've got a given element and a different number of oxygens. So in a series with 2 oxyanions, the lesser one is going to be the ite, and the one with the higher number is the ate. Right? So remember the ick. Right, that's the higher one. You ate too much and you got ick. That's how I was tying those together. Usually it just comes with memorizing these things. All right, so let's look at a couple examples. Most of them are going to be these oxyanions. You've got oxygen and something else, like oxygen and nitrogen. You've got nitrate and nitrite. And with sulfur, you have sulfate and sulfite. Right? Like these guys show up in wine, right? Warning, contains sulfites. The reason why they put that in there is it is a suspected carcinogen. They did a meta-study with chewing tobacco and lip cancer, and they saw reduced rates of lip cancer with people in Nordic countries who were using a product called snus, which is still an oral tobacco, but that didn't have the sulfites and nitrites that went into some of the processing for regular old American chaw. So these lower compounds are sometimes bad for you. Notice that when a series of oxoanion contains different numbers of oxygen, the oxoanions are named according to the number of oxygen atoms in the ion. The one with more oxygen, that's the ate. The one with fewer becomes the ite. If you've got some that are going to have up to four different oxygens in there, and 4 of them, right? If there's more than 2, then you're going to use prefixes, hypo, meaning less than, like a hypodermic needle, and per, like hyperactive, meaning more than. So you've got ClO-, which is hypo, less than chlorite. So here's our chlorite, right? And then I've got our chlorate, and then you've got perchlorate. And you can have hypobromite, bromite, bromate, and perbromate. This is a table that shows our common polyatomic ions. Now, in exam number 2, the first time you're going to come across these, I will probably, but not 100%, give you this table, right? So it is highly likely that you will see this the first time around, and I will give it to you. You do not necessarily have to memorize this, but it would sure help. I'm not going to say like memorize all the perchlorates and stuff, but knowing these guys after you work with them for a while is certainly going to be very, very helpful for you. We've got a couple of different groups on here. All right. First up, you've got this lone guy by itself, right? It's a polyatomic cation. That's really the only polyatomic cation you're going to see is ammonium. Right? It's got an IUM at the end, and it's NH4+. So regular ammonia is NH3 neutral. Ammonium has picked up a hydrogen, and it's got a plus charge to it, and we call it ammonium. That's pretty much our only common polyatomic cation. The rest are all going to be anions, right? And we're going to classify them whether they got single, double, or triple charges. Lots of single charge guys, acetate. So acetic acid, the conjugate base for that is acetate. A lot of these do exist as acid-base conjugate pairs. Cyanide, Cn minus. We've got chlorite and chlorate and perchlorate. These and hypochlorite. These are all going to be -1. Dihydrogen phosphate, hydrogen carbonate, hydrogen sulfate, hydroxide. Right, that's what makes something a base is hydroxide. Permanganate, nitrite, and nitrate. Nitrates are really common. We will see those a lot because all nitrates are soluble. Doubly charged are going to be carbonate, chromate, dichromate, peroxide, hydrogen phosphate, sulfite, sulfate, and thiosulfate. And then we got a triply charged guy down here that's phosphate. Are there more singly charged anions out there? Yes. Doubly charged? Sure. Triply charged? You betcha. But these are just the ones that are the most common. Okay? So when we name these guys, we're still going to follow the same rules for combining them with a metal or a cation. Right? We're still going to leave our cation the way it is, and then our anion, we're going to come in with the ending that indicates what charge state we've got. So nitrate versus nitrate, or how many oxygens we've got, nitrate versus nitrite. So we could come up with ammonium nitrate. Right? That's useful in making gunpowder or as a fertilizer. Or you could have sodium cyanide if you wanted to kill somebody, right? Or you could have potassium thiosulfate or potassium permanganate or sodium phosphate. Right? Those are all common chemicals that you will see. Right? You can do that as both type 1 and type 2. Right? So sodium hydroxide, right? This is our go-to strong base, Na, OH, we're going to form 1 + 1 and a -1, NaOH is our formula, right? Magnesium carbonate, Mg's got a 2+, carbonate's got a -2 charge, it's going to be MgCO3. Sodium carbonate, on the other hand, right, that's going to show up in baking, I was getting confused, baking soda, baking powder, the one with the yellow box and the arm on it, not the red box with the Indian on it. The charge on here is 2, so we're going to need 2 sodiums, Na2CO3. Iron 2 hydroxide. We're going to take our iron 2+, right, because this guy's got a 2. We're going to do iron 2+, and our hydroxide is going to be -1, so it'll be Fe, and then we'll put parentheses around it, 2, right, to indicate that these guys are traveling as a group, and I've got twice as many OHs. Here, with our carbonate, it's only one carbonate group. I don't need to put parentheses around it. If, as practice, you want to kind of keep those training wheels on during homework sessions or during studying, I will probably know what you mean, but if it's just the one thing by itself, right, and there's an imaginary 1 coefficient down here, you don't need to put the parentheses around it, and you don't need to put the parentheses around it over here. Now, if you had like ammonium, like with 2 ammoniums on it, then yeah, you would. You'd need to like indicate that if this was ammonium carbonate, it would be NH, maybe parentheses, NH4, close parentheses, subscript 2, CO3. Yep. Let's name some of these guys. So we've got sodium, we've got Na2SO4, KH2PO4, FeNO3, 3, MnOH2, Na2SO3, Na2CO3. So let's look at these. So Na2SO4 is going to be sodium. We don't need to worry about the 2 in here because it's going to balance out with the sulfate in only one possible way. You go with sulfate, and we just look that up on our table. Right? This guy over here is a little tricky. That's potassium dihydrogen, because I got 2 sulfate. Now it's a phosphate. Potassium, that's a phosphate, not a sulfate. Here we've got iron 3 nitrate. We got nitrate's going to act like a -1. We've got 3 of them, so our iron has to be a +3 charge. So we'll do it as iron, parentheses, III, nitrate. Magnesium hydroxide, manganese hydroxide, it's a transition metal. It can exist in more than one state. The hydroxides are always going to be -1. We've got 2 of them, so we've got -2 charge. Our manganese has to have a plus charge, so we'll do it as manganese, parentheses, 2 hydroxide. Our sodium sulfite, our sulfite is always going to be -2, moving around together. Our sodium, to balance that, we're going to need 2 of them. We don't need to put any parentheses or anything to say how many sodiums, because there's only one way that it's going to be neutral, so sodium sulfite. And here's sodium carbonate, same sort of thing, except we've got a carbonate instead of a sulfate. Right? Okay. Looking at binary covalent compounds, this is type 3. Right? Our third type is going to be between 2 nonmetals. Not always, but often. And these are things that are going to be able to form in a way that's similar to binary ionic compounds, but these are going to be covalent. Covalent compounds made out of 2 things. When we do that, there is often more than one ratio we can get with these molecules. So here we've got N2O, right? I'm combining nitrogen and oxygen. I can do it as N2O, NO, NO2, N2O3, N2O4, N2O5. I've got different ways we can combine these 2 elements, right? And so I need to say, well, how many of each kind, right? Again, your hint is that it's going to be between 2 different non-metallic elements, but not always, right? And I need to specify then and say how many nitrogens I've got and how many oxygens I've got. So the systematic name here would be dinitrogen, because I've got 2, and then monoxide. It tells me how many oxides. You could also get away with leaving off the mon a lot of time and call it like dinitrogen oxide. The common name is nitrous oxide. NO is going to be nitrogen monoxide. You don't have to call it monnitrogen, or nitric oxide. NO2 is going to be nitrogen dioxide, because I've got 2 oxygens. N2O3 will be dinitrogen trioxide. Di for 2, tri. So it's going to follow those Greek roots like mono, di, tri, tetra, penta, hexa, octa, penta, hepta, oxa, nona, deca, undeca, dodeca. I don't know, as many as you need, right? N2O5 is going to be dinitrogen pentoxide, dinitrogen tetroxide. Right? So if you've got time, I would suggest you look into the dihydrogen monoxide conspiracy. And so dihydrogen monoxide is going to have how many hydrogens and how many oxygens? Okay? So a certified container for dihydrogen monoxide should carry a warning label that looks like this. It could also be called hydroxylic acid, hydroxy acid, hydrogen hydroxide, hydrogen oxide. Dihydrogen monoxide is tasteless, colorless, and odorless. Inhalation can lead to severe dyspnea and internal injuries. Avoid contact with electrical equipment. Prolonged exposure in its solid form causes severe tissue damage, may cause severe burns, right? Especially in the gas phase. It can cause diaphoresis, micturition, and acute tissue hydration. So Jeff, here's poor Jeff. Right? Jeff has been a professional athlete for over 10 years, and for 7 he has been taking dihydrogen monoxide to increase his endurance. And Jeff is now addicted. Without dihydrogen monoxide, he will die in 3 days. There is no cure. So forget vaccines. The real danger is dihydrogen monoxide. It's a major component in acid rain. Prolonged exposure causes tissue damage in solid form, contributes to soil erosion, lethal in quantities above 1 liter per liter of body weight. Each year it contributes directly to millions of deaths. It has a higher pH than any other acid out there. All right, so be careful of dihydrogen monoxide. All right. Molecular compounds. They're going to be composed of 2 or more nonmetals most of the time. So you're going to write the name of the element with the smallest group number first. If the 2 elements lie in the same group, then you write the element with the greatest row number first. So basically, toppest and leftist goes first. The prefixes given to each element indicate the number of atoms present. So you wouldn't call it dioxide mononitrogen, right? You do mononitrogen dioxide or something. So we're going to do a prefix indicating the number, name of the first element, prefix, second element gets that IDE ending. So these prefixes are the same used in naming hydrates. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Right? If there is only one atom in the first element, you can leave the mono off. Right. So N2O4, the first element is listed as the more cation-like, so further leftist. The second element is more anion-like, and you're going to stick the IDE ending on it. And then you add a prefix to indicate the number of each atom. So dinitrogen, tetra, or oxide. Those on the ending. So looking at some more examples, let's name each of these compounds. PCl5 is going to be phosphorus pentachloride. Phosphorus pentachloride. PCl3 is going to be phosphorus trichloride. SO2 is going to be sulfur dioxide. And you guys are all familiar with like carbon monoxide and carbon dioxide, right? So you guys have come across those at some point in your past, right? So here's a flow chart for naming our binary compounds. So first, is it a binary compound? Does it have a metal, right? If no, then it's a type 3 and we got to use those prefixes. If yes, it's got a metal, does that metal form more than one cation? Nope, it's a simple guy. We're going to use just the metal name. So we're going to use the metal name for the cation. If it is more than one cation, so something like iron, which could be 2+ or 3+, you determine the charge and use Roman numerals to indicate what that charge is. Let's look at another example. Given the following systematic names, go for the formula. So vanadium 5-fluoride, dioxygen difluoride, rubidium peroxide, and gallium oxide. For vanadium fluoride, we know that the vanadium is going to have a +5 charge. Fluorine is always going to have a -1 charge, so our formula is going to be VF5. For our dioxygen difluoride, oxygen is going to go to the left. It's more cation-like. Fluorine is more anion-like. It's going to be dioxygen, so O2, and then difluoride, F2. Rubidium peroxide, since rubidium is group 1A, it's only going to form +1. Thus, the 2 rubidium ions need to balance out the -2 charge on the peroxide ion, O2, 2-. So we're going to end up with Rb2O2. Now I want Rbs. Gallium oxide is going to be Ga2O3. Since gallium is in group 3, it's only going to form +3, just like aluminum, which means it's going to be 3+. Oxygens are going to be 2-. So drop and swap, gallium-2O3. We also have rules for naming acids. A lot of these compounds are going to be acidic. In molecules in which one or more of those H+ ions are attached to an anion, and they are labile, meaning they're able to detach themselves and float around in solution, we've got an acid. So if the name of the anion ends in "ide," the acid is named with the prefix hydro and the suffix -ic. So, for example, hydrochloric acid, that's your go-to strong acid. Hydrochloric is going to be HCl. Hydroiodic would be HN iodine, HI. The names of the oxygen-containing anions are based on the root name of the anion along with "ic" or "us." So you can have sulfuric acid or sulfurous acid or nitric acid or nitrous acid. If it ends in "ate," you get the "ic," right? You ate too much, you got "ic." If the name ends in "ite," you keep the "ite." The "ite" is going to be replaced with "us." So nitrite becomes nitrous acid, and if I've got nitrate, it becomes nitric acid. let's look at some of these examples. HClO4, you've got perchlorate as the anion, which means you get perchloric acid. HClO3, one less oxygen, is going to be chlorate, becomes chloric acid. HClO2, chlorite, becomes chlorous acid. HClO, hypochlorite, becomes hypochlorous acid. These guys in here, right, hydrofluoric, hydrochloric, hydrobromic, hydroiodic, hydrocyanic, got a CN minus, hydrosulfuric acid, not to be confused with plain old ordinary sulfuric acid, or sulfurous acid, or phosphoric acid, or acetic acid. Here is our flowchart for naming these acids. Does the anion contain oxygen? No. Then it's going to be hydro, whatever the anion is, hydrofluoric acid, right? Does it contain oxygen? Right? So it's an oxygen-containing compound like nitrate, right? Yes. Do you check it whether it's an ite or an ate? Right? If it's an ite, it becomes us. So hydrochlorous acid. Right, or hydro, and then if it has 8, then it becomes an ic, like nitrate becomes HNO3, becomes H-nitrate, becomes nitric acid. Okay. That is it for chapter 3. So next chapter will be chapter 4, and we'll start looking at putting these guys into 3 dimensions.